Hello there, and welcome to the Sleepy Library. Tonight, we are going on a journey through time, a slow and gentle exploration of how the ground beneath our feet has wandered across the face of our planet for billions of years. The continents we call home, the familiar shapes we see on maps, are not fixed in place. They have traveled unimaginable distances, collided with tremendous force, and split apart in geological ballet that unfolds over millions upon millions of years. This is the story of continental evolution, told in a way that invites you to rest, to let your mind wander through deep time, and to find comfort in the ancient rhythms of our restless Earth. Close your eyes if you wish, and imagine the planet as it existed long before any human walked upon it, before any creature left its footprint, before even the first plants colonized the land. Imagine a world where the continents you know did not exist in their current form, where oceans covered different parts of the globe, and where the very rocks beneath mountains were once ocean floors. This is a journey measured not in years or centuries, but in epochs spanning hundreds of millions of years. There is no rush here, only the patient unfolding of geological time. Let yourself settle into a comfortable position, allowing your body to relax completely. As we travel through the history of our planet's moving continents, let each fact, each image, each description wash over you like gentle waves. There is nothing to memorize, nothing to strain to understand. Simply let the words carry you along, painting pictures in your mind of a planet that has been reshaping itself since long before life emerged from the oceans, and will continue reshaping itself long after we are gone. The story we are about to explore is one of the most profound in all of science. It reveals that our world is not static, but wonderfully, beautifully, endlessly dynamic. The solid ground that seems so unchanging is actually flowing, moving, transforming across timescales so vast that they dwarf human comprehension. And yet, understanding this movement can bring a deep sense of peace, a recognition that we are part of something far larger than ourselves, connected to processes that have shaped Earth for eons. Our story begins with a fundamental truth about our planet, one that might seem surprising at first. The solid ground beneath us, which feels so permanent and unchanging, so reliable and stable, is actually in constant motion. The Earth's outer layer, called the lithosphere, is broken into enormous pieces called tectonic plates. These plates, some the size of entire continents, others smaller but still vast beyond human scale, float upon a layer of partially molten rock known as the asthenosphere. This deeper layer is not quite liquid, not quite solid, but somewhere in between, a thick, viscous material that flows like honey warmed by the sun, though infinitely slower and under pressures we can scarcely imagine. The tectonic plates move at speeds so slow that in a human lifetime they travel only about as far as your fingernails grow. Some plates move as slowly as 10 millimeters each year, a pace so gradual that no instrument could detect it in a single day, or even a single year, without the most sophisticated technology. Other plates creep along at speeds of 160 millimeters annually, which sounds faster, but is still extraordinarily slow. About as fast as your hair grows if you never cut it. This is geology measured in the pace of growth we can barely perceive, a reminder that the most profound changes often happen too slowly for any single generation to witness. Picture these tectonic plates as giant rafts carrying continents and ocean floors across the surface of our planet. Imagine them as pieces in a planetary puzzle that never stops rearranging itself, each piece moving according to forces deep within the Earth. 7 major plates dominate the Earth's surface, carrying most of the continents and the Pacific Ocean. The North American plate carries an entire continent, from the frozen Arctic to the warm Caribbean, and part of the Atlantic Ocean floor stretches eastward toward Europe. The Eurasian plate holds Europe and most of Asia, a vast expanse containing countless mountain ranges, river systems, and the homes of billions of people, all riding together on this single piece of Earth's crust. The African plate supports the entire African continent and portions of the surrounding oceans, moving northward in a slow collision with Europe that builds the Alps higher with each passing year. The Antarctic plate cradles the frozen continent at the bottom of the world, isolated and slowly moving, preserving in its ice and rock the memory of warmer times when it was connected to other landmasses. The South American plate bears that vast continent and its adjacent ocean floor, carrying the Amazon rainforest, the Andes Mountains, and Patagonian plains on its slow westward journey. The Australian plate carries Australia and its surrounding waters northward towards Southeast Asia, a journey that has been ongoing for tens of millions of years and will continue for millions more. And the Pacific plate, the largest of all, encompasses most of the Pacific Ocean floor, a vast expanse of oceanic crust slowly being created at its eastern edge and consumed at its western boundary. Beyond these 7 major plates are 8 smaller ones, each playing its own role in the intricate dance of continental motion. The Philippine plate, the Juan de Fuca plate, the Cocos plate, the Caribbean plate, the Arabian plate, the Indian plate, the Nazca plate, and the Scotia plate all contribute to the complex geometry of Earth's moving surface. There are even smaller microplates, fragments and slivers of crust caught between the larger plates, being pushed and pulled in complex patterns that geologists are still working to fully understand. These plates do not move randomly, scattered about without purpose or pattern. They are driven by the slow churning of the Earth's mantle, the thick layer of hot rock that lies beneath the crust. The mantle makes up the vast majority of Earth's volume, a region nearly 3,000 kilometers thick, extending from just below the crust all the way down to the boundary with the liquid outer core. Deep within this mantle, heat from the core warms the bottom layers, causing the rock there to become less dense and rise, much like warm water rises to the surface in a pot on the stove, or like warm air rises on a summer day. As this heated rock reaches the base of the lithosphere, having risen through hundreds or thousands of kilometers of mantle, it spreads sideways, moving horizontally beneath the crust like a great river of stone, flowing at a pace measured in centimeters per year. As it moves, the rock cools gradually, losing heat to the cooler material above it. Eventually, having traveled far from its point of origin, the cooled rock becomes denser than the surrounding material and begins to sink back down toward the core, completing the circuit. This sinking rock will eventually be heated again and begin the cycle anew, rising, spreading, cooling, sinking, in an endless circulation that has continued for billions of years and will continue for billions more. This endless circulation, called mantle convection, is the engine that drives the continents across the face of the Earth. It is a heat engine, powered by the warmth radiating from Earth's core, which itself is heated by the slow radioactive decay of elements like uranium and thorium deep within the planet. This process is so slow, so gradual, that the half-life of these radioactive elements is measured in billions of years. Yet their decay provides just enough heat to keep the mantle churning, to keep the plates moving, to keep Earth geologically active. The movement is so gradual so gentle in its pace, that if you could stand in one spot for your entire life, watching and waiting, you would never feel the ground shift beneath your feet. The motion is utterly imperceptible at human timescales. You could spend 100 years standing on the same rock, and you would detect no movement at all. Your children could stand there for their entire lives, and their children after them, generation after generation, and still the motion would be too slow to observe directly. Yet over millions of years, these imperceptible movements add up to journeys of thousands of kilometers. Continents that once nestled together, sharing borders and ecosystems, have moved to opposite sides of the planet. Ocean basins that once existed, teeming with life and covering vast expanses, have vanished completely, consumed by the Earth's interior and recycled into new rock. Mountain ranges that once rivaled the Himalayas in height and grandeur have eroded away to gentle hills, their peaks ground down by wind and water and ice over hundreds of years, millions of years. New mountains have risen where none existed before, thrust upward by the collision of continents or the volcanic activity at plate boundaries. All of this unfolds in what geologists call deep time, a scale so vast that the entire span of human civilization, from the first cities to the present day, is but a fleeting instant, barely a heartbeat in the long life of the planet. For centuries, people looked at maps and noticed something curious, something that seemed almost too remarkable to be coincidence. The coastlines of South America and Africa seemed to fit together like pieces of a puzzle, as if someone had torn them apart and scattered them across the ocean. The eastern edge of South America, with its distinctive bulge near Brazil, appeared to nestle perfectly into the western coast of Africa, matching curve for curve like two pieces of a jigsaw puzzle separated and set aside. The more carefully people looked, the better the fit appeared to be, especially if they considered not the current coastlines, but the edges of the continental shelves, the submerged margins of the continents hidden beneath shallow seas. But this observation remained nothing more than a curiosity, an interesting coincidence noted by mapmakers and geographers, but not seriously considered by scientists until the early 20th century. It was then that a German meteorologist named Alfred Wegener began to take the idea seriously. Wegener was not a geologist by training. He was a scientist who studied weather and climate, and he had traveled to Greenland to study polar conditions. But he had a curious mind and was not afraid to think across disciplinary boundaries, to ask questions that specialists in one field might not think to ask. In 1912, Wegener proposed a revolutionary theory that would eventually transform our understanding of the Earth. He suggested that all of Earth's continents had once been joined together in a single massive landmass, which he called Pangaea, meaning all lands in ancient Greek. This wasn't just a poetic name, but a description of what Wegener believed had existed. Literally, all the land on Earth joined into one supercontinent. According to Wegener's idea, this supercontinent had remained intact until approximately 200 million years ago, when it began to break apart. The fragments, he proposed, had slowly moved across the globe like icebergs floating on the ocean, eventually arriving at the positions we see today. Wegener supported his theory with multiple lines of evidence, building a case that drew from geology, paleontology, and climatology. He pointed to the matching coastlines of continents now separated by vast oceans, showing that the fit was too good to be mere chance. He noted that identical fossils of ancient plants and animals were found on continents thousands of kilometers apart, separated by oceans that those organisms could never have crossed. One particularly compelling example, Mesosaurus, a small freshwater reptile that lived about 280 million years ago. Fossils of this creature, which was only 1 meter long and adapted to life in lakes and rivers, were found exclusively in southern Africa and South America. Since Mesosaurus was a freshwater animal and could not have survived in salt water, it could not possibly have crossed the Atlantic Ocean. The only reasonable explanation was that Africa and South America had once been connected, allowing Mesosaurus to spread across both regions before they separated. Wegener also found evidence in the rocks themselves, in the very structure of the continents. Certain geological formations in South America matched formations in Africa with remarkable precision, not just in general appearance, but in specific details. The types of rocks, their ages determined through various dating methods, and their structures, the way they were folded or faulted, all corresponded in ways that strongly suggested they had formed as part of a single continuous landmass. Mountain ranges that ended abruptly at one coastline seemed to pick up again on another continent across the ocean, as if a single range had been split in two. Ancient river valleys appeared to line up when the continents were placed side by side. Additionally, Wegener discovered evidence of ancient glaciation in places that are now tropical, evidence that the climate in these regions had once been dramatically different. Coal deposits, formed from ancient tropical plants that grew in warm, swampy environments, were found buried in Antarctica, the frozen continent at the bottom of the world. This discovery suggested that this ice-covered land had once been positioned much closer to the equator, in a warmer climate where lush vegetation could thrive and accumulate into the thick layers that eventually became coal. Similarly, rocks in Africa and South America showed evidence of ancient glaciation. Scratch marks and deposits left by ice sheets, even though these regions are now far too warm for glaciers to exist. Despite this compelling evidence, which Wegener presented in lectures and papers throughout the 1910s and 20s, the scientific community largely rejected his theory. The rejection wasn't because scientists didn't find his evidence interesting or thought-provoking. Many acknowledged that the fit of the continents was intriguing and that the fossil evidence was difficult to explain by other means. The main criticism, and it was a substantial one, was that Wegener could not explain the mechanism, could not describe how continents could possibly plow through the solid rock of the ocean floor. The very idea seemed physically impossible. The ocean floor was made of solid rock, dense and rigid. How could continents, also made of solid rock, push through it like ships moving through water? Wegener suggested that the Earth's rotation might generate forces strong enough to move continents, an idea he called the pole-fleeing force. He proposed that the rotation of the Earth might cause continents to move toward the equator, away from the poles. He also proposed that the gravitational pull of the Sun and Moon might contribute to continental movement, providing a kind of tidal force that could drag continents across the surface. These were creative ideas, showing Wegener's willingness to think boldly. But calculations by physicists quickly showed that these forces were far too weak to move such enormous masses of rock. The centrifugal force from Earth's rotation and the tidal forces from the Sun and Moon, while real, were simply not strong enough to overcome the resistance of solid rock. Without a convincing mechanism to explain how continents could move, most scientists dismissed the theory as interesting speculation, but ultimately implausible. Wegener spent the rest of his life searching for additional evidence to support his theory, traveling to remote regions, studying rocks and fossils, corresponding with other scientists who shared his interest. He was convinced he was right, that the evidence was too strong to ignore, even if he couldn't yet explain the mechanism. Tragically, he perished during an expedition across the Greenland ice cap in 1930, caught in a blizzard while attempting to bring supplies to a remote research station. He was only 50 years old. He never lived to see his ideas vindicated, never knew that within a few decades of his passing, his theory would be transformed from a controversial hypothesis into the foundation of modern geology. For decades after Wegener's passing, continental drift remained controversial, accepted by some geologists, especially in the southern hemisphere, where the evidence seemed particularly strong, but rejected by many others, particularly in North America, where the geological establishment was most skeptical. The theory seemed to explain so much: the matching coastlines, the fossil distributions, the ancient climates. Yet without a mechanism, it remained incomplete. But new discoveries were on the horizon. Discoveries made possible by new technologies developed during and after World War II. Discoveries that would vindicate Wegener's vision and transform our understanding of how the Earth works. The breakthrough came from an unexpected place, from studying not the continents but the bottom of the ocean, a realm that had been almost completely unexplored until the middle of the 20th century. After World War II, new sonar technology, originally developed to detect submarines, allowed scientists to map the ocean floor with unprecedented detail. Ships crisscrossed the oceans, sending sound waves down to the sea floor and measuring how long it took for the echoes to return, building up a picture of the underwater landscape. What they discovered was astounding, completely unexpected, and ultimately revolutionary. Running down the middle of the Atlantic Ocean was an enormous underwater mountain range, later named the Mid-Atlantic Ridge. This ridge stretched for thousands of kilometers from north to south, running roughly parallel to the coastlines of the Americas on one side and Europe and Africa on the other. It was not a single mountain, but a continuous chain of underwater peaks and valleys, rising thousands of meters above the surrounding ocean floor. The ridge was split down its center by a deep valley, a rift where the crust appeared to be pulling apart. Similar ridges were found in other oceans, eventually revealing a continuous system of underwater mountains that snaked around the entire planet for more than 80,000 kilometers, the longest mountain range on Earth. These mid-ocean ridges marked something profound, the places where new ocean floor was being born. The ridges weren't just passive features on the seafloor, but active zones of volcanic and seismic activity, places where Earth's internal heat was escaping to the surface and creating new crust. In 1960, an American geologist named Harry Hess, who had spent World War II commanding a naval vessel and using its sonar to map the ocean floor, proposed a theory to explain these underwater mountains. He suggested that molten rock, or magma, was continuously welling up from deep within the Earth at these ridges. When the magma reached the cold seawater, typically just above freezing at the depth of the ocean floor, it rapidly cooled and solidified, forming new oceanic crust made primarily of a dark volcanic rock called basalt. This newly formed crust then slowly moved away from the ridge on both sides, like two conveyor belts running in opposite directions. Hess called this process seafloor spreading. The implications were profound and far-reaching. If new ocean floor was constantly being created at mid-ocean ridges, then the ocean basins were not static features that had existed unchanged for billions of years, relics of Earth's formation that had merely filled with water. Instead, they were young, dynamic structures, constantly being renewed, with ocean floor being created, moving, and eventually being destroyed in a great cycle. The oldest rocks found on the ocean floor were only about 200 million years old, far younger than the ancient rocks found on continents, some of which are over 4 billion years old, dating back to almost the very beginning of Earth's history. This meant that old ocean floor must be disappearing somewhere, recycled back into the Earth's interior. The mechanism for this recycling was found at the deep ocean trenches, the deepest parts of the ocean floor, places where the seafloor plunges down into narrow, deep valleys. At these trenches, oceanic crust was being forced downward beneath either another oceanic plate or a continental plate, in a process called subduction. As the old, cold oceanic crust descended into the hot mantle, it eventually melted and was reabsorbed, its materials recycled into the Earth's interior, completing the cycle. New crust formed at mid-ocean ridges, old crust destroyed at trenches. The ocean floors were in a state of perpetual renewal, a planetary recycling system operating on a timescale of hundreds of millions of years. Further evidence came from studying the magnetism preserved in oceanic rocks, a discovery that provided some of the most convincing proof of seafloor spreading. As molten rock cools and solidifies at mid-ocean ridges, magnetic minerals within it, tiny crystals of iron-rich minerals, align themselves with Earth's magnetic field, like tiny compass needles freezing in place as the rock hardens. Scientists discovered something remarkable about Earth's magnetic field. It reverses itself at irregular intervals, with the North Magnetic Pole becoming the South Pole and vice versa. These reversals happen unpredictably, sometimes after a few 100,000 years, sometimes after millions of years, but they leave a permanent record in rocks that form when the field has a particular orientation. When scientists mapped the magnetic patterns in oceanic rocks, towing magnetometers behind ships and measuring the magnetic properties of the seafloor, they found alternating stripes of normal and reversed magnetism running parallel to the mid-ocean ridges. These stripes were perfectly symmetrical on both sides of the ridge, like a mirror image, with each stripe on one side matching a stripe of the same age and magnetic orientation on the other side. This pattern could only mean one thing. The rocks on both sides of the ridge had formed at the same time and had moved away from the ridge at the same speed, exactly as Hess had predicted. The seafloor spreading hypothesis was confirmed by this elegant evidence. These discoveries provided the missing piece of Wegener's puzzle, the mechanism he had been unable to explain. Continents weren't ploughing through the ocean floor at all. Instead, they were riding on tectonic plates that were being pushed apart by the creation of new ocean floor at mid-ocean ridges, and pulled together by the destruction of old ocean floor at subduction zones. This new understanding gave birth to the theory of plate tectonics, which unified seafloor spreading and continental drift into a comprehensive explanation of how the Earth's surface moves and changes over geological time. Armed with this new understanding, scientists could now reconstruct the history of continental movements with remarkable precision. The story of Pangaea, the supercontinent that Wegener had envisioned, became clearer and more detailed. By studying the ages and magnetic properties of rocks on different continents, by mapping the distribution of fossils and ancient climate indicators, by tracing the scars of ancient collisions and the remnants of vanished oceans, geologists could trace how the continents had moved over hundreds of millions of years, creating an animated history of Earth's changing face. Pangaea began to assemble approximately 335 million years ago, during a period called the Carboniferous, named for the vast coal deposits that formed during this time from the remains of enormous swamp forests. Various smaller continents and land masses slowly converged, driven by the movements of tectonic plates. The process took tens of millions of years, as ancient oceans gradually closed and land masses collided. When continents collide, their edges don't slide past each other smoothly, but instead crumple and buckle, like two cars colliding in slow motion, creating massive mountain ranges. The formation of Pangaea gave rise to several great mountain chains, including the ancestral Appalachian Mountains, which once stood as tall as the modern Himalayas. their peaks soaring 6,000 meters or more into the sky. By approximately 250 million years ago, near the end of a period called the Permian, Pangaea had reached its maximum extent. Nearly all of Earth's landmass was joined together in a single continuous continent, shaped roughly like a giant letter C. This supercontinent stretched from pole to pole, with the bulk of its mass in the southern hemisphere. Surrounding Pangaea was a single vast ocean called Panthalassa, which covered most of the planet's surface, a body of water so enormous that it made all of today's oceans combined seem modest by comparison. Between the arms of the C-shaped continent lay a smaller ocean basin called the Tethys Sea, which would play an important role in future continental movements. The interior of Pangaea was unlike any environment that exists today, a landscape of extremes that would have been challenging for most forms of life. Imagine vast areas, hundreds or even thousands of kilometers from the nearest ocean, far beyond the reach of any sea breeze or maritime influence. These inland regions experienced extreme temperatures, blistering hot in summer when the sun beat down relentlessly on the dry land, and freezing cold in winter when there was no nearby ocean to moderate the temperature. Rainfall was scarce in the continental interior, creating enormous deserts that stretched across the heart of the supercontinent. Vast, sandy wastes where only the most hardy and specialized organisms could survive. Only along the coasts, where moist ocean air could reach, could more temperate conditions exist, creating a narrow band of more habitable climate around the edges of the supercontinent. For life, Pangaea presented both challenges and opportunities, a mixed blessing that shaped the evolution of many lineages. With all land connected, plants and animals could migrate freely across the globe without crossing oceans, spreading from one end of the supercontinent to the other over generations. Species that evolved in one part of Pangaea could potentially spread to nearly every other part of the supercontinent, limited only by climate and geography rather than by water barriers. This explains why fossils of certain creatures are found on multiple continents today. They were all connected when those organisms lived, allowing them to disperse widely across Pangaea. But Pangaea was not destined to remain whole, not fated to persist forever as a single landmass. The same forces that had brought the continents together also contained the seeds of their separation. Deep beneath Pangaea, heat from the Earth's mantle began to accumulate, trapped beneath the thick blanket of continental crust. Unable to escape easily through the thick, insulating layer of continent above, this heat eventually caused the supercontinent to dome upward, bulging like a blister on the Earth's surface. Cracks formed in the crust as it stretched and bulged under the pressure of rising mantle rock. Molten rock pushed up through these cracks, erupting from volcanoes and filling vast areas with lava, creating volcanic regions that would later become markers of where the continent began to split. Over millions of years, these cracks widened into valleys, then into seaways, as ocean water began to flood in, and finally into true oceans with spreading ridges and all the features of modern ocean basins. The breakup of Pangaea began approximately 200 million years ago, during the Triassic period, the dawn of the age of dinosaurs. The first major rift opened between what would become Africa and South America, a crack that would eventually widen into the South Atlantic Ocean. Molten rock poured out along this rift, forming new oceanic crust and beginning the creation of a new ocean basin. At first, the rift was narrow, perhaps only a few hundred kilometers wide, creating a long, narrow seaway similar to the modern Red Sea, which is itself a young ocean in the early stages of formation. Shallow seas flooded in from Panthalassa, the great surrounding ocean, bringing marine life into the new basin. But as millions of years passed, the rift continued to widen, and the Atlantic grew larger and larger, pushing Africa and South America farther and farther apart. Around 180 million years ago, during the Jurassic period, when dinosaurs dominated the land and the first birds took to the air, Pangaea split into two large landmasses. The northern portion, called Laurasia, included what would become North America, Europe, and most of Asia, a vast landmass that stretched across the northern hemisphere. The southern portion, called Gondwana, consisted of South America, Africa, Antarctica, Australia, India, and Madagascar, encompassing most of the southern hemisphere's landmass. Between them lay the growing Tethys Ocean, a seaway that separated the northern and southern portions of the former supercontinent. The separation continued, driven by the relentless forces of mantle convection and seafloor spreading. About 150 million years ago, during the Jurassic period, Gondwana itself began to fragment, no longer able to hold together as a single landmass. The first piece to break away was the combined landmass of India and Madagascar, which separated from the rest of Gondwana and began moving northward across the Tethys Ocean, embarking on a journey that would eventually carry India into collision with Asia. Africa and South America remained joined for millions more years, connected along what would become their Atlantic coastlines, sharing ecosystems and species. But eventually, they too began to separate, the forces of rifting finally overcoming the strength of the continental crust that bound them together. A triple junction formed during this separation, a place where three rift systems met, radiating outward from a central point like the spokes of a wheel. Two of these rifts continued to open, creating the South Atlantic Ocean between South America and Africa, and opening the passage between Africa and Antarctica. The third rift, which extended into what is now Central Africa, failed to fully develop into an ocean basin and became what geologists call a failed rift or orlicogen, a scar on the continent marking where rifting began but did not complete. By about 100 million years ago, during the Cretaceous period, when flowering plants were beginning to diversify and dinosaurs still ruled the Earth, South America had fully separated from Africa, and the South Atlantic Ocean was opening from south to north like a zipper slowly unfastening. Meanwhile, India continued its remarkable journey northward, a sprint by geological standards. It separated from Madagascar around 100 million years ago and began racing toward Asia at speeds of up to 15 centimeters per year, exceptionally fast for tectonic motion, covering thousands of kilometers in just tens of millions of years. Australia began to separate from Antarctica roughly 80 million years ago, slowly rotating and moving northward toward the equator, beginning a journey that continues today. The Atlantic Ocean continued to widen, its mid-ocean ridge pushing North America and Europe apart at a slow but steady pace. By about 60 million years ago, just after the extinction of the dinosaurs, had opened new ecological opportunities for mammals. Greenland had begun to separate from Europe, and the North Atlantic was fully open, a new ocean basin connecting the Arctic Ocean to the waters of the Central Atlantic. The continents were now recognizably similar to their modern positions, though they would continue to move for tens of millions of years more, slowly arranging themselves into the configuration we see on today's maps. Throughout this long separation, the fragments of Pangaea carried with them evidence of their shared history, clues that would later allow scientists to reconstruct the story of the supercontinent. Matching geological formations, identical fossils, and corresponding rock types all testified to their ancient connection. The jigsaw puzzle that Wegener had observed, the remarkable fit of the continents, was the remnant of Pangaea's breakup. Continents that had once been neighbors, now separated by thousands of kilometers of ocean, yet still retaining the shape of their ancient boundaries. Not all tectonic motion results in continents moving apart, in the creation of new ocean basins and the widening of seaways. Sometimes, plates carrying continents converge, moving toward each other rather than away, and when they do, the collision creates some of the most spectacular geological features on Earth. The Himalayan mountain range, home to the world's highest peaks including Mount Everest, tells the story of one of the most dramatic continental collisions in Earth's history, a slow-motion crash that continues even today. About 80 million years ago, the Indian subcontinent, having broken away from Gondwana and separated from Madagascar, was an island continent moving rapidly northward across the Tethys Ocean. It traveled at extraordinary speeds for tectonic motion, covering roughly 6,400 kilometers in just 80 million years, a rate that would seem glacially slow by human standards, but is remarkably fast by the standards of plate tectonics. Ahead of it lay the southern margin of the Eurasian continent, ancient and stable, unaware of the impending collision. When India finally collided with Eurasia between 40 and 50 million years ago, approximately 10 million years after the extinction of the dinosaurs, something remarkable happened. Unlike oceanic crust, which is dense and easily subducted into the mantle, sinking beneath lighter continental or oceanic crust, continental crust is lighter and more buoyant, filled with minerals that make it float higher on the mantle. When two continents collide, neither can easily sink beneath the other. They are too buoyant, too light, too resistant to being forced down into the mantle. Instead, the collision causes the crust to crumple, fold, and thrust upward, like two carpets being pushed together on a floor, buckling and rising up into wrinkles and folds. The collision between India and Eurasia was not a single catastrophic event, not a moment when two landmasses smashed together and immediately formed mountains. Rather, it was a slow-motion crash that unfolded over millions of years and continues today, a process so gradual that it can only be understood by studying rocks and measuring movements with precise instruments. As the two landmasses pressed together, the sediments that had accumulated on the floor of the Tethys Ocean were squeezed and lifted upward, compressed between the converging continents. Layers of rock that had formed peacefully on the ocean floor, accumulating grain by grain over millions of years, were thrust high into the air, twisted and folded by the immense forces at work, transformed from horizontal beds into vertical or even overturned layers. Some rocks that had formed deep in the Earth's crust, under pressures and temperatures far exceeding anything found to the surface, were pushed up to altitudes of over 8,000 meters above sea level. The result was the Himalayan mountain range, stretching for about 2,400 kilometers from east to west, a wall of peaks separating the Indian subcontinent from the Tibetan plateau. Within this range stands Mount Everest, called Chomolungma in Tibetan and Sagarmatha in Nepali, the highest point on Earth's surface at 8,848 meters above sea level. The summit of Everest is made of limestone, rock that formed from the compressed remains of marine organisms that once lived in the Tethys Ocean. Now pushed to an altitude where the air is too thin for most forms of life to survive, where climbers need supplemental oxygen to avoid losing consciousness. Embedded in these rocks are fossils of ancient marine creatures, crinoids and ammonites, and other organisms that lived in warm tropical seas. Silent witnesses to the mountain's oceanic origins, reminders that the roof of the world was once the floor of an ocean. But the Himalayas tell only part of the story of this great collision. North of the Himalayas lies the Tibetan Plateau, a vast, elevated region covering about 2.5 million square kilometers, roughly 6 times the size of California, or 10 times the size of the United Kingdom. The entire plateau sits at an average elevation of over 4,000 meters above sea level, making it the highest and largest plateau on Earth, a region sometimes called the roof of the world. This immense uplift occurred because India did not simply push into Eurasia like a ship running aground, but actually slid partway beneath it, thickening the continental crust in the collision zone and causing the entire region to rise like bread dough expanding in an oven. Recent research using magnetic data from ancient rocks suggests the collision was even more complex than previously thought, involving not just 2 continents meeting, but multiple oceanic plates and subduction zones playing roles in the process. Scientists have found evidence that an oceanic plate called the Kshiroda Plate may have existed between India and Eurasia, adding another layer of complexity to the collision. The convergence appears to have occurred in stages rather than as a single event, with volcanic island chains and smaller landmasses being caught up and incorporated into the growing mountain range. Their rocks now found jumbled together with oceanic sediments and continental material in the complex geology of the Himalayas. The collision is not over, not finished, not a completed event in Earth's history. India continues to push northward, moving at about 40 to 50 millimeters per year, still driving into Eurasia like a slow but unstoppable force. This ongoing convergence means the Himalayas are still rising, still being pushed upward by the relentless pressure of India's northward journey, though erosion from wind, water and ice continuously wears them down, carrying their material away to be deposited in the plains of India and Bangladesh. The net effect, balancing uplift against erosion, is that some peaks grow by nearly 10 millimeters per year, slowly gaining altitude even as other parts of the range are worn away. At the same time, the collision generates tremendous stress in the Earth's crust, pressure that builds up over years or decades or centuries until it is suddenly released in earthquakes. The Himalayan region experiences frequent seismic activity, earthquakes large and small, including some of the most powerful and destructive earthquakes in recorded history. These earthquakes are the price of mountain building, the cost of the ongoing collision, a reminder that the forces shaping our planet are still very much active. The pressure of India pushing into Eurasia has consequences that extend far beyond the immediate collision zone, affecting regions thousands of kilometers away. Much of Asia is being squeezed eastward toward the Pacific Ocean, pushed aside by the advancing Indian plate. Tibet is pressed from the south by India and hemmed in from the north by the rest of Asia, creating a zone of intense deformation where the crust is being compressed, extended, and sheared in complex patterns. Faults crisscross the region, great fractures in the Earth's crust that accommodate the ongoing motion, allowing blocks of crust to slide past each other and relieve some of the tremendous stress. Some research suggests that the Indian plate may actually be splitting beneath Tibet, tearing into 2 pieces as it descends into the mantle, with different portions behaving differently as they sink, creating a complex 3-dimensional structure deep underground. Continental collisions have occurred throughout Earth's history, each one creating mountains and reshaping the planet's surface. The Appalachian Mountains in North America, the Atlas Mountains in North Africa, the Ural Mountains that divide Europe from Asia, and the Alps in Europe all formed through similar processes, when ancient continents crashed together during the assembly of past supercontinents. Each collision created not just mountains, but also changed the climate, affected ocean circulation patterns, and influenced the evolution of life by creating new habitats at different elevations and forming barriers that isolated populations and drove evolutionary change. While continents collide in some places, building mountains and deforming crust, they pull apart in others, and the process of their separation creates new ocean basins through the mechanism of seafloor spreading. This process, which operates at mid-ocean ridges throughout the world's oceans, is responsible for creating new oceanic crust and driving the movement of continents. Understanding this process helps us see how continents move and how the Earth continuously renews its surface. At a mid-ocean ridge, the seafloor is pulling apart, separating like a seam coming undone. The forces causing this separation come from deep within the Earth, driven by the convection currents in the mantle that we discussed earlier. As the lithospheric plates move apart, pulled by the weight of dense sinking slabs elsewhere, and pushed by rising mantle material beneath the ridge, the pressure on the rocks beneath the ridge decreases. This reduction in pressure causes the hot rocks of the upper mantle to begin melting, even though their temperature hasn't changed. It's a process called decompression melting, similar to how water boils at lower temperatures at high altitudes where the pressure is reduced. The molten rock, or magma, is less dense than the solid rock around it, filled with gas bubbles and lighter minerals, so it rises toward the surface, buoyant like oil in water, accumulating beneath the ridge in chambers and channels. Eventually, the magma finds its way through cracks and fissures to erupt onto the ocean floor, emerging from volcanic vents and fissures. When this hot magma, with temperatures of over 1,000 degrees Celsius, encounters the frigid seawater, typically just above freezing at the depth of the ocean floor, it cools rapidly, almost instantly in geological terms, solidifying into new oceanic crust, made primarily of a dark volcanic rock called basalt, the same type of rock that forms volcanic islands like Hawaii and Iceland. This process doesn't happen all at once, not in great catastrophic bursts, but continuously and remarkably consistently. At fast-spreading ridges, like the East Pacific Rise off the coast of South America, new crust forms at rates of up to 16 centimeters per year, with magma erupting frequently and creating smooth, relatively gentle topography. At slow-spreading ridges, like the Mid-Atlantic Ridge that runs down the center of the Atlantic Ocean, the rate is only 2 to 5 centimeters per year, with less frequent eruptions and more rugged, faulted terrain. But whether fast or slow, the process never truly stops. Day after day, year after year, millennium after millennium, new ocean floor is created at these underwater volcanic mountain ranges, adding to the Earth's crust. As new crust forms at the ridge axis, at the very center of the spreading zone, it pushes older crust away on both sides, moving in opposite directions like two conveyor belts. The newly formed crust is hot, less dense because it's still warm and thermally expanded, and stands higher than older crust, creating the elevated topography of the mid-ocean ridge. But as it moves away from the ridge, it cools gradually, contracts, becomes denser, and subsides, sinking lower into the mantle. This is why mid-ocean ridges stand elevated above the surrounding ocean floor, typically about 2,000 meters higher, creating underwater mountain ranges that would be spectacular if we could see them above water. It's also why the ocean floor gets progressively deeper with distance from the ridge. Predictable pattern that follows a mathematical relationship between age and depth. The crust is older, farther from the ridge, colder and denser, so it sits lower in the mantle, creating the deep, abyssal plains that cover most of the ocean floor. The rate of seafloor spreading can be measured with remarkable precision using the magnetic stripes we mentioned earlier. As magma cools at the ridge, magnetic minerals within it, align with Earth's magnetic field, creating a record of the field's orientation. Because Earth's magnetic field reverses periodically, the ocean floor preserves these reversals in alternating stripes of normal and reversed magnetism. By mapping these magnetic stripes, identifying which ones correspond to which magnetic reversals, and knowing when those reversals occurred from dating rocks on land, scientists can calculate exactly how fast the seafloor has been spreading and trace the history of ocean basin formation back through time. Seafloor spreading explains why oceanic crust is so young compared to continental crust, a puzzle that geologists struggled with before plate tectonics was understood. The oldest ocean floor yet discovered is about 200 million years old, found in the far western Pacific, ancient by human standards, but young in geological terms. By contrast, rocks on continents can be over 4 billion years old, dating back almost to the formation of the Earth itself, preserving a record of nearly the entire history of our planet. The reason for this dramatic difference is that oceanic crust is constantly being created and destroyed in the plate tectonic cycle. New ocean floor forms at ridges, spreads away, and is eventually consumed at subduction zones, where it sinks back into the mantle. The entire ocean floor is recycled roughly every 200 million years, meaning that no oceanic crust older than this remains. This recycling maintains Earth's overall size, a crucial aspect of plate tectonics that makes the whole system work. If new crust were continuously created at mid-ocean ridges, without old crust being destroyed somewhere else, the planet would steadily expand, growing larger over time. Some scientists in the early days of plate tectonics actually proposed this, suggesting that Earth was expanding, and that's why the continents were moving apart. But careful measurements showed that Earth has remained essentially the same size for billions of years, meaning that crust creation at ridges must be balanced by crust destruction at subduction zones. It's a beautiful equilibrium, a planetary-scale recycling system that has operated for eons, maintaining the balance between creation and destruction. The creation of new ocean floor doesn't just affect the oceans, doesn't just create underwater mountains and abyssal plains. As seafloor spreading pushes oceanic plates outward from ridges, those plates carry continents with them, like passengers on a raft. The Atlantic Ocean is currently widening at about 2.5 centimeters per year as new crust forms at the mid-Atlantic ridge, a rate so slow as to be imperceptible but inexorable. This means Europe and North America are moving apart at roughly the same rate that your fingernails grow, a comparison that helps us grasp just how slow yet relentless this process is. South America and Africa are likewise moving apart as the South Atlantic spreads, driven by the same process. In another 200 million years, if current trends continue and the Atlantic keeps spreading, the ocean could be twice as wide as it is today, with the Americas even farther from Europe and Africa than they are now. We don't need to look only to the distant past or to the deep ocean to see continental processes in action, to witness the forces that shape our planet. In Eastern Africa, we can observe a continent beginning to split apart right now, in real time, a process that offers a window into how continents break up and how new oceans are born. The East African Rift System is one of the most geologically active regions on Earth, a place where the continent is quite literally tearing itself apart, creating a scar that runs for thousands of kilometers from north to south. The rift system extends from the Afar Triangle in Ethiopia, a low-lying region where 3 tectonic plates meet, southward through Kenya with its dramatic rift valley, through Tanzania with its volcanic peaks and soda lakes, and into Mozambique, creating a zone of volcanoes, earthquakes, and dramatic topography. It's actually two parallel rift systems, the Eastern Rift and the Western Rift, which together form what geologists call the East African Rift. The rifts are characterized by long valleys bounded by steep escarpments, cliffs that mark where blocks of crust have dropped down along faults, chains of volcanoes that mark where magma is rising from below, and numerous lakes that have formed in the depressed areas, filling the valleys with water. What's happening here is that the African continent is being pulled apart by forces in the mantle below, by rising currents of hot rock that are pushing up on the base of the lithosphere. Hot material rising beneath Africa is causing the continent to dome upward and stretch, like a piece of plastic wrap being pulled from underneath. As the crust stretches and thins, it becomes weaker and cracks form, fractures that develop into faults along which sections of crust can move. These cracks develop into faults, along which sections of crust drop downward, creating the rift valleys, deep linear depressions that can be hundreds of kilometers long and tens of kilometers wide. The process is similar to how Pangaea began to break up 200 million years ago, but we're witnessing it in its early stages, seeing the birth of a rift that might one day become an ocean. The East African Rift is pulling apart at a rate of about 6 to 7 millimeters per year, measured precisely using GPS satellites that can detect tiny movements of the Earth's surface. That might not sound like much, barely more than the width of a pencil lead each year, but over millions of years, it adds up substantially. If this rifting continues at its current rate, and that's a big if, because geological processes can slow down or speed up over time, the eastern portion of Africa, carrying the Horn of Africa, Somalia, and Madagascar, will eventually separate completely from the main African continent. Seawater will flood into the Rift Valley from the Red Sea to the north or the Indian Ocean to the east, and a new ocean will be born, similar to how the Atlantic Ocean formed when Pangaea split apart 200 million years ago. Evidence for this ongoing rifting is everywhere in the region, written into the landscape in ways that geologists can read. Volcanoes dot the landscape, fed by magma rising from below, taking advantage of the cracks in the crust to reach the surface. Some of these volcanoes are among the most active on Earth, like Nyiragongo in the Democratic Republic of Congo, which contains a lava lake in its crater, a pool of molten rock that glows red at night. Hot springs and geysers indicate that hot rock lies not far beneath the surface, heating groundwater that then rises to create thermal features. Earthquakes are common as sections of crust shift and adjust along the faults, releasing the stress that builds up as the continent stretches. The region's distinctive geography of long, narrow lakes, like Lake Tanganyika and Lake Malawi, exists because these lakes occupy rift valleys, the down-dropped sections between parallel faults, creating some of the deepest lakes in the world. The rifting process has been ongoing for about 25 million years, and could continue for tens of millions more before the separation is complete. This is geology operating at its typical pace, slow and patient, transforming continents over timescales that make human history seem like a brief moment. Eventually, perhaps 50 to 100 million years from now, the separation will be complete, and a new ocean, sometimes informally called the East African Ocean, will separate what was once a single continent. The Somali Plate, carrying the eastern portion of Africa, including Somalia and parts of Kenya and Tanzania, will become an island continent, much as India was when it broke away from Gondwana 80 million years ago and began its journey northward toward Asia. This ongoing continental rifting demonstrates that the processes which shaped Earth in the past are still operating today. That plate tectonics is not something that happened long ago, but continues in the present. The movement of continents, the formation of new ocean basins, the building of mountains, all of these are ongoing processes, unfolding too slowly for us to perceive directly in our daily lives, but unmistakably visible in the geological record and measurable with modern instruments. We are living on an active, dynamic planet, and the continents are still moving beneath our feet. While new ocean floor forms at mid-ocean ridges and continents rift apart in places like East Africa, old ocean floor meets its end at subduction zones, regions where oceanic crust is forced down into the mantle and recycled. The most extensive and active system of subduction zones encircles the Pacific Ocean, forming what is dramatically known as the Ring of Fire, a zone of earthquakes and volcanoes that marks the boundaries where plates converge. The Ring of Fire is a roughly horseshoe-shaped zone of intense volcanic and seismic activity stretching about 40,000 kilometers around the Pacific Basin. It includes the western coasts of North and South America, from Alaska to Chile, the Aleutian Islands that arc across from Alaska toward Russia, the eastern coast of Asia from Russia through Japan to the Philippines, and extends through Indonesia, New Zealand, and the islands of the South Pacific, creating a nearly continuous belt of active tectonics. Approximately 90% of the world's earthquakes and 75% of the world's active volcanoes occur along the Ring of Fire, making it the most geologically active region on Earth. The reason for this concentration of geological activity is subduction, the process by which oceanic crust sinks back into the mantle. The Pacific Ocean floor, created at mid-ocean ridges such as the East Pacific Rise, spreads outward until it encounters continental margins or other oceanic plates. Being denser than continental crust, because it's composed primarily of basalt, a dense volcanic rock, the oceanic plate descends beneath the lighter continental plate and plunges back into the mantle at an angle, typically dipping at 30 to 60 degrees. This process releases enormous amounts of energy and creates the conditions for both earthquakes and volcanic eruptions. As the oceanic plate descends into the mantle, it carries with it water and other materials from the ocean floor. Water trapped in cracks and pores, water bound up in minerals that formed on the sea floor, sediments scraped from the descending plate. As the plate goes deeper and deeper, it heats up, warmed by the surrounding mantle. At depths of roughly 100 to 200 kilometers, the combination of heat and increasing pressure causes water to be released from minerals in the descending plate, driven out like water squeezed from a sponge. This water rises into the wedge of mantle rock above the subducting plate, lowering the melting temperature of that rock in the same way that salt lowers the melting temperature of ice. The result is the generation of magma, molten rock that is more buoyant than its surroundings and rises through the overlying plate, eventually erupting at the surface to form volcanoes. The volcanoes of the Ring of Fire include some of the most famous and dangerous on Earth, mountains that have become legendary for their powerful eruptions. Mount Fuji in Japan, a nearly perfect cone that has become a symbol of that nation. Mount St. Helens in Washington State, which erupted catastrophically in 1980. The volcanoes of Indonesia, including Krakatoa, which erupted in 1883 with such force that the explosion was heard thousands of kilometers away. The Andes Mountains in South America, a chain of volcanoes stretching along the entire western edge of the continent. All of these owe their existence to subduction, to oceanic crust sinking beneath continental crust and generating magma. These volcanoes tend to be explosive, producing eruptions that can devastate vast areas. Because the magma they produce is different from the basaltic magma at mid-ocean ridges. It's more viscous, thicker and stickier, and gas-rich, leading to violent eruptions that can produce pyroclastic flows, avalanches of hot gas and ash that race down mountainsides at hundreds of kilometers per hour. Subduction zones are also where most of the world's largest and most destructive earthquakes occur, releasing energy equivalent to thousands or even millions of atomic bombs in a matter of seconds. As the oceanic plate descends, it doesn't slide smoothly past the overlying plate. Instead, it sticks and binds against it, the two plates locked together by friction, with stress building up over decades or centuries or even longer. Eventually, the stress becomes too great, exceeding the strength of the rocks, and the plates suddenly slip past each other, releasing the accumulated energy in seconds. The result is an earthquake, sometimes of catastrophic magnitude, powerful enough to destroy cities and reshape landscapes. The boundary between plates at a subduction zone can be hundreds of kilometers long, and when it ruptures during a great earthquake, the entire length may move at once, creating a massive release of energy. These are the earthquakes that generate the most powerful seismic waves, shaking that can be felt hundreds or even thousands of kilometers away. And when they occur beneath the ocean, can create tsunamis, giant waves that devastate coastal areas. The 2011 Tohoku earthquake in Japan, which generated a tsunami that caused the Fukushima nuclear disaster. The 2004 Indian Ocean earthquake and tsunami, which affected 14 countries and caused hundreds of thousands of casualties. The 1960 Chilean earthquake, the most powerful ever recorded at magnitude 9.5. All occurred at subduction zones around the Ring of Fire, testament to the enormous energies involved in plate tectonics. Yet, despite the dangers, subduction zones are essential to plate tectonics and the evolution of continents. Without subduction, old ocean floor would accumulate, and either the Earth would have to expand to accommodate all the new crust being created at mid-ocean ridges, or plate motion would have to cease entirely. Subduction provides the force that pulls plates apart at mid-ocean ridges and drives much of the motion of tectonic plates. The descending slab of oceanic crust, acting like a weight, pulling the rest of the plate along. It's also at subduction zones that new continental material can be created, as volcanic arcs built on the edge of continents add new rock to the continental crust, gradually growing continents over geological time. The Ring of Fire is not unique in Earth's history. Not the first time that subduction zones have surrounded an ocean basin. Subduction zones have existed throughout geological time, sometimes surrounding supercontinents, just as the Ring of Fire now surrounds the Pacific. When Pangaea existed 200 million years ago, a ring of subduction zones surrounded it, marking the edge where the supercontinent met the vast Panthalassa Ocean, the predecessor to the Pacific. As Pangaea broke apart, the pattern of subduction shifted, with some zones dying out as new ones formed, creating the configuration we see today. In the future, the pattern will shift again as the continents continue to move and ocean basins open and close. Mountains are among Earth's most inspiring landforms, their peaks reaching toward the sky, their slopes carved by ice and water into shapes of great beauty, their heights challenging human endurance and stirring the imagination. Many of the world's great mountain ranges owe their existence to the collision of tectonic plates, and each range tells a story of continents meeting, of ocean floors consumed, and of rock forced upward by unimaginable pressures. The Himalayas, as we have discussed, formed when India collided with Eurasia, But they are not the only mountains created by continental collision. The Alps, stretching across several European countries from France to Austria, arose when the African plate pushed northward into the Eurasian plate. The collision began about 35 million years ago and continues today, with Africa still moving northward, though at a rate of only a few millimeters per year. Like the Himalayas, the Alps were formed by the crumpling and folding of rock layers as the continents converged, with some rocks being thrust many kilometers from their original position. The beautiful parallel ranges and valleys of the Alps reflect the folding and faulting that occurred during the collision, creating a landscape that has inspired artists, writers, and mountaineers for centuries. The Appalachian Mountains in eastern North America are far older, ancient mountains that have been worn down by hundreds of millions of years of erosion. They formed during the assembly of Pangaea, when a series of continental collisions occurred over a period spanning from about 480 million to about 280 million years ago. During this time, several ancient continents and smaller landmasses converged, each collision pushing up mountains. When these continents collided, they pushed up enormous mountains, ranges that may have rivaled the modern Himalayas in height, with peaks soaring to heights of 6,000 meters or more, crowned with glaciers and snow. But the Appalachians are ancient mountains, and erosion has been working on them for hundreds of millions of years since their formation. Wind, water, ice, and gravity have all played their part in wearing them down from towering peaks to the gentle, rounded forms we see today. The highest point in the Appalachians is now Mount Mitchell in North Carolina, at 2,037 meters. Respectable, but far lower than the ancient peaks that once stood here. What remains are the eroded roots of once great mountains, their rocks telling stories of ancient collisions and the assembly of Pangaea, their minerals and structures providing clues to the forces that shaped them. The Ural Mountains, which divide Europe from Asia, stretching from the Arctic Ocean to the steppes of Kazakhstan, also formed during the assembly of Pangaea, when two ancient continents, Laurussia and Siberia, collided about 300 million years ago. The Atlas Mountains in North Africa formed more recently, pushed up by the collision of Africa with Europe that also created the Alps. Each range preserves in its rocks evidence of the forces that created it, compressed and folded layers showing how the crust was shortened, fault lines where blocks of crust moved past each other, and metamorphic rocks that were transformed by heat and pressure deep underground, their minerals recrystallized, and their structures changed by the intense conditions they experienced. Mountain building is not just about height, not just about creating tall peaks that challenge climbers and inspire awe. When continents collide and mountains rise, they affect climate, ocean circulation, and the evolution of life in profound ways. The uplift of the Himalayas and Tibetan Plateau, for example, has had effects on Asian weather patterns that can hardly be overstated, creating the monsoons that bring life-giving rain to billions of people, altering atmospheric circulation patterns across half the planet. Mountains create barriers that channel wind and precipitation, creating wet climates on their windward sides where moist air is forced upward and cooled, causing rain or snow to fall, and rain shadows on their leeward sides where dry air descends, creating deserts. They provide diverse habitats at different elevations, from tropical lowlands through temperate forests to alpine tundra and permanent ice, supporting unique communities of plants and animals adapted to each zone. Mountains also drive erosion, becoming their own agents of destruction even as they rise. As peaks rise, gravity and weather attack them relentlessly. Rivers carve deep valleys, carrying sediment down from the mountains to be deposited in lowlands and deltas, building up thick sequences of sedimentary rock. Glaciers form on high peaks, grinding rock into fine powder and carving U-shaped valleys with their immense weight and power. Chemical weathering breaks down minerals, consuming carbon dioxide from the atmosphere in the process, and eventually carrying dissolved minerals to the ocean. Over millions of years, mountains that rose from continental collisions are gradually worn away. Their material spread across the continents and carried to the ocean, where it may one day be recycled into new rock. But as long as the collision continues, as long as the plates keep converging, new rock is pushed upward to replace what is eroded away, and the mountains persist, locked in a battle between uplift and erosion that can last for tens of millions of years. Looking at Earth from space, astronauts see a beautiful blue and white sphere, swirled with clouds, its surface showing the familiar shapes of continents and oceans, green and brown lands surrounded by blue seas. But this view represents only a snapshot in time, a single frame in a billions of years long film of continental motion. If we could watch the Earth in time-lapse, speeding up geological time so that millions of years passed in seconds, compressing deep time into human comprehensible durations, we would see the continents in constant motion, moving across the surface of the globe like pieces on a board game that rearranges itself. We would see Pangaea assembled piece by piece as continents converged from all directions, then watch it break apart again, fragments scattering across the face of the planet like a puzzle being disassembled. We would see oceans appear where none existed before, starting as narrow rifts that widened into seaways and then into vast ocean basins. And we would see other oceans vanish where they once stretched for thousands of kilometers, consumed by subduction as continents converged. We would watch mountain ranges rise and then slowly erode away, their peaks worn down by wind and water and ice, until they were reduced to gentle hills. India would race across the Tethys Ocean at what would appear to be breakneck speed before crashing into Asia in slow motion. The Atlantic would open like a zipper, unfastening, slowly at first, then steadily widening year after year, millennium after millennium, pushing the Americas away from Europe and Africa. Australia would detach from Antarctica and slide northward toward the equator, rotating as it moved, gradually approaching Southeast Asia. This motion continues today, right now, even as you rest and listen to these words. The continents are not frozen in their current positions, but are steadily moving, carrying us along as passengers on these massive rafts of rock. North America and Europe are moving apart at about 2.5 centimeters per year, widening the Atlantic Ocean by a few centimeters annually, an amount that seems tiny but adds up to thousands of kilometers over millions of years. The Pacific Ocean is shrinking, narrowing as subduction consumes its edges faster than new crust forms at its ridges, though this process will take millions of years to complete. Africa is splitting along the East African Rift, slowly creating what will eventually become a new ocean, though the separation won't be complete for tens of millions of years. The Himalayas are still rising, still being pushed upward by India's northward journey, gaining a few millimeters in height each year. Australia is moving northward at about 6 to 7 centimeters per year, gradually approaching Southeast Asia, though it will take millions of years for them to potentially collide. These movements, imperceptible in a human lifetime, invisible to direct observation, add up over geological time to journeys of thousands of kilometers. In the 50 million years since the extinction of the dinosaurs, India has moved over 4,000 kilometers northward, covering a distance equivalent to the width of the United States. In the 150 million years since the Atlantic began to open, North America and Europe have moved thousands of kilometers apart, creating an ocean basin that now separates continents that were once joined. If we project these motions into the future, extrapolating current trends while acknowledging the uncertainties involved, we can predict, at least roughly, where the continents will be in millions of years to come, though the details remain uncertain because mantle convection patterns can change and new rifts can form in unexpected places. Just as continents have come together and moved apart in the past, assembling into supercontinents and then fragmenting again, they will do so again in the future. The forces that drive plate tectonics, the heat flowing from Earth's core and the convection of the mantle, show no signs of stopping, no indication that they will cease in the foreseeable future. As long as Earth's interior remains hot, and it will remain hot for billions of years to come, the tectonic plates will continue to move, and continents will continue their slow dance across the surface of the planet, assembling and dispersing in an endless cycle. Scientists have developed several scenarios for how the continents might move in the future, using computer models that simulate mantle convection and plate motions. These predictions are based on extrapolating current plate motions and understanding the cycles of supercontinent formation and breakup that have occurred in the past. While the details are uncertain, because we cannot predict exactly how mantle convection will evolve over hundreds of millions of years, many researchers think that the next supercontinent will form sometime in the next 200 to 300 million years. One proposed future supercontinent is called Pangaea Proxima, meaning the next Pangaea in Latin. This scenario, developed by geologist Christopher Scottese, suggests that the Atlantic Ocean will eventually stop widening and begin to close, reversing its current trend. Subduction zones would develop along the eastern margins of the Americas, where currently there is only passive margin, consuming the Atlantic seafloor and pulling the continents back together. Over millions of years, the Americas would move eastward, eventually colliding with Europe and Africa, recreating something like the configuration that existed when Pangaea was intact. Meanwhile, Australia would continue moving northward, eventually colliding with Southeast Asia and becoming part of the larger landmass. The result would be a new supercontinent, roughly ring-shaped, encircling an interior sea, with most of the world's landmass assembled into a single vast continent located primarily in the northern hemisphere. In this scenario, the interior of Pangaea Proxima would likely be extremely arid, even more so than the interior of the original Pangaea, with vast deserts covering much of the landmass, hot and dry, and inhospitable to most forms of life. Only the coastal regions and areas near the interior sea would receive enough moisture to support rich ecosystems, creating a stark contrast between the verdant coasts and the barren interior. The formation of such a supercontinent would have profound effects on climate, potentially causing mass extinctions among species adapted to current conditions. Ocean circulation patterns would be completely transformed, and the distribution of heat around the planet would change dramatically. However, Pangaea Proxima is just one possibility, one scenario among several that geologists have proposed. Another scenario, called Amasia, suggests a different configuration based on different assumptions about how plates will move. In this model, proposed by researchers studying mantle flow patterns, the Pacific Ocean would close rather than the Atlantic, consumed by subduction around its entire rim. The Americas would move westward, eventually colliding with Asia, while Europe and Africa would remain relatively stationary but shift northward. The resulting supercontinent would form around the North Pole, centered on the current Arctic Ocean, which would be completely enclosed by land. Amasia would be a polar supercontinent, quite different from Pangaea Proxima, with different climate patterns and different implications for life. A third possibility is called Aurica, proposed by other researchers, in which both the Atlantic and Pacific Oceans would close, consumed by subduction, while new ocean basins would form in other locations, perhaps splitting Eurasia or opening new seaways through other continents. In this scenario, the continents would assemble in yet another pattern, different from either Pangaea Proxima or Amasia, demonstrating that the future configuration of Earth's land masses remains genuinely uncertain, subject to changes in mantle convection that we cannot fully predict. Recent research supports the Amasia scenario, suggesting it might occur within 200 to 300 million years. Studies of mantle flow, patterns, and the movement of tectonic plates indicate that the Pacific is closing faster than the Atlantic is opening. Subduction around the Pacific Rim, consuming oceanic crust at a rate that exceeds the creation of new crust at the East Pacific Rise, which could lead to the Americas eventually colliding with Asia rather than returning to Europe and Africa. But this is speculation, educated guessing based on current trends, and the reality may turn out to be something no one has yet imagined. Regardless of which scenario proves correct, several things seem likely about Earth's future. The formation of a new supercontinent would dramatically alter Earth's climate, creating extreme conditions in the interior regions. Large interior areas would experience extreme temperatures and aridity, potentially leading to mass extinctions among species adapted to current conditions, particularly mammals, which have difficulty surviving in very hot climates. The collision of continents would build enormous mountain ranges, possibly exceeding the height of the current Himalayas, creating new barriers to circulation and new habitats at high elevations. Volcanic activity would increase as subduction zones consumed oceanic crust and produced magma, adding greenhouse gases to the atmosphere. Ocean circulation patterns would be completely transformed, affecting the distribution of heat around the planet and potentially causing dramatic climate shifts. But a new supercontinent, like those before it, would not be permanent, would not last forever. After forming, it would persist for perhaps 100 million years, maybe more, maybe less, before beginning to rift apart again, pulled asunder by heat accumulating beneath it. New oceans would open, continents would separate, and the cycle would begin anew, repeating the pattern that has occurred at least 3 times before in Earth's history. This is the supercontinent cycle, a recurring pattern in Earth's history that has shaped our planet's surface for billions of years and will continue to shape it for billions more. The concept of a supercontinent cycle, in which continents periodically assemble and disperse in a great rhythm spanning hundreds of millions of years, is one of the great insights of modern geology. By studying the geological record, examining ancient rocks and their magnetic properties, mapping the distribution of fossils, and matching geological formations across continents, scientists have identified at least 3, and possibly more, supercontinents that existed before Pangaea. Each formed through the convergence of smaller landmasses, persisted for a time as a single great continent, then broke apart, only to have the fragments eventually reassemble into a new supercontinent in a different configuration. The oldest well-documented supercontinent is called Columbia, or Nuna, which assembled approximately 1.8 billion years ago, during a time called the Paleoproterozoic era, when life consisted only of single-celled organisms and there were no plants or animals. Evidence for Columbia comes from matching geological provinces on different continents, rock formations that appear to have been joined when they formed, but are now separated by oceans, suggesting they were once part of a single landmass. Columbia persisted for several hundred million years before beginning to break apart around 1.5 billion years ago, fragmenting into smaller continents that drifted apart. After Columbia's breakup, the continental fragments moved apart, creating new ocean basins, then gradually came back together over hundreds of millions of years to form another supercontinent called Rodinia. This assembly occurred around 1.1 billion years ago, during the late Precambrian, when life was still entirely microbial and the atmosphere contained very little oxygen. Rodinia's configuration is still debated among geologists, with different reconstructions showing different arrangements, but most show a large central landmass with various smaller continents attached around the edges. Rodinia began to break up around 750 million years ago, and its fragmentation may have triggered a series of ice ages known as snowball Earth events, periods when glaciers covered much or even all of the planet's surface, creating the most severe ice ages in Earth's history. The fragments of Rodinia moved apart over hundreds of millions of years, creating new oceans and new configurations of continents, before beginning to converge again around 600 million years ago. This convergence led to the formation of several large land masses, including Gondwana, which assembled approximately 600 million years ago and included most of the continents that would later form the southern part of Pangaea, South America, Africa, Antarctica, Australia, India, and Madagascar. Another landmass, sometimes called Laurasia, would eventually form Pangaea's northern portion, including North America, Europe, and Asia. These landmasses finally came together around 300 million years ago to create Pangaea, the supercontinent we've discussed extensively, which then broke apart beginning about 200 million years ago to create the current configuration of continents. The cycle from one supercontinent to the next takes between 300 million and 600 million years, a vast span of time that makes even the entirety of human history seem like a brief moment. The process is driven by mantle convection, by the endless circulation of hot rock rising and cold rock sinking that we discussed earlier. When a supercontinent forms, it acts like a thick blanket covering part of Earth's surface, insulating the mantle below and preventing heat from escaping efficiently. Heat accumulates beneath the supercontinent, unable to escape through the thick continental crust, eventually causing the mantle to rise in a plume, like a bubble rising in a pot of water that's being heated from below. This rising mantle plume pushes the supercontinent upward, causing it to dome and crack, stretching the crust until fractures form. The cracks develop into rifts. The rifts widen into ocean basins as new crust forms, and the supercontinent breaks apart, its fragments scattering across the globe. As the fragments move apart, cold oceanic crust forms between them, spreading away from mid-ocean ridges. Eventually, this old, cold, dense crust begins to sink at subduction zones, its weight pulling it down into the mantle. The pull of this sinking crust helps to draw the continents back together, providing much of the force that drives plate motion. Meanwhile, on the opposite side of the planet from where the supercontinent broke up, continents may begin to converge, driven by subduction and mantle flow patterns that favor assembly in a different location. Over hundreds of millions of years, a new supercontinent assembles, often in a different location than the previous one, perhaps on the opposite side of the planet, and the cycle begins again, with heat accumulating beneath the new supercontinent. This supercontinent cycle has profound implications for life on Earth, influencing evolution in ways that are still being understood. Each assembly and breakup affects global climate, creating new environmental conditions that species must adapt to or perish. Ocean chemistry changes as circulation patterns are altered by the new arrangement of continents. The distribution of nutrients in the ocean shifts, affecting the productivity of different regions. The carbon cycle is influenced by the amount of coastal area, the rate of mountain building, and the extent of subduction. Even the oxygen content of the atmosphere can be affected by changes in the burial of organic matter and the weathering of rocks. Some researchers have suggested that the supercontinent cycle may even directly influence the evolution of complex life, providing the environmental variety and selective pressures that drive innovation. The breakup of Rodinia, for example, occurred shortly before the Cambrian explosion, a period roughly 540 million years ago, when most major groups of animals first appeared in the fossil record, a time of extraordinary evolutionary innovation. The fragmentation of the supercontinent created new coastlines, new shallow seas, new environmental gradients that may have provided opportunities for organisms to diversify and adapt. Similarly, the assembly and subsequent breakup of Pangaea reshaped ecosystems and influenced the evolution of many groups of organisms, including the rise of mammals after the extinction of the dinosaurs, when the continents were already well separated and evolving their own unique faunas. Throughout this journey through the evolution of continents, one theme emerges again and again: the vastness of geological time, the immensity of the timescales on which these processes operate. The processes we have described unfold over millions and tens of millions and hundreds of millions of years, durations so long that they challenge human comprehension. To a human, whose lifespan is measured in decades, these timescales are almost incomprehensible, beyond our direct experience. Our entire recorded history, from the first written records to the present day, spans only a few thousand years, a blink of an eye on the geological timescale. The entire existence of our species, Homo sapiens, is measured in hundreds of thousands of years, perhaps 300,000 years since our species first emerged in Africa. Even the time since the extinction of the dinosaurs, which seems like ancient history to us, is a mere 66 million years, barely more than 1% of Earth's 4.5 billion year history. Yet, the movement of continents, the opening and closing of oceans, the rise and erosion of mountains, all happen at these vast, slow timescales that dwarf human experience. Continents move at rates measured in millimeters or centimeters per year, speeds comparable to the growth of fingernails or hair, so slow as to be imperceptible without careful measurement. Mountain ranges rise slowly, their uplift measured in millimeters per year, often balanced by erosion, so that the net gain in height is even smaller, requiring millions of years to create the highest peaks. Ocean basins open over tens of millions of years, widening by a few centimeters annually, requiring 100 million years to grow from a narrow rift to an ocean the size of the Atlantic. These rates seem glacially slow, and indeed, that phrase captures the reality quite well. For glaciers also move slowly, creeping down valleys at speeds ranging from a few centimeters to a few meters per day, depending on their size and the steepness of their slopes. Yet, given enough time, measured in thousands or tens of thousands of years, glaciers can carve deep valleys, reshape entire landscapes, and leave their mark on the land in ways that persist long after the ice has melted. Similarly, the slow movement of continents, given enough time, measured in millions or hundreds of millions of years, can reshape the entire surface of the planet, moving land masses from pole to equator, creating and destroying oceans, building and eroding mountain ranges. One of the challenges in understanding geological time is that we have no direct experience of it, no intuitive grasp of such vast durations. We cannot watch continents move or mountains rise in a human lifetime. We cannot see seafloor spreading or subduction with our own eyes. These processes happen too slowly for human perception, unfolding at rates that require instruments and careful measurement to detect. But we can see their effects written into the rocks, read the stories they tell in layers of sediment and folded strata, measure the current motions of plates with GPS satellites, and reconstruct what has happened over millions of years. From these observations, we build an understanding of how the Earth works, piecing together a story of continental motion that spans billions of years. Modern technology has made it possible to measure plate motions directly, to observe the movement that was once only inferred from geological evidence. GPS satellites orbiting overhead can detect the movement of points on Earth's surface with millimeter precision, measuring positions so accurately that changes of just a few millimeters can be detected over the course of a year. By measuring the positions of GPS receivers installed on different continents over several years, scientists can determine how fast and in what direction each tectonic plate is moving. These measurements confirm what geologists inferred from studying rocks. The continents are indeed moving, spreading apart at mid-ocean ridges and converging at subduction zones, at just the rates predicted by the theory of plate tectonics. Seismology, the study of earthquakes and the seismic waves they generate, provides another window into plate tectonics. The distribution of earthquakes around the globe clearly outlines the boundaries between tectonic plates, marking the zones where plates interact. Earthquakes at mid-ocean ridges are shallow and relatively small, typically occurring at depths of less than 10 kilometers, reflecting the creation of new crust and the brittle fracture of young, cooling rock. Earthquakes at subduction zones are more varied, some shallow where the plates first meet, some at intermediate depths of 50 to 300 kilometers as the plate descends, some very deep, occurring at depths at up to 700 kilometers, tracing the path of the descending oceanic plate as it sinks into the mantle. Earthquakes at transform faults, where plates slide past each other horizontally, have their own characteristic patterns, typically occurring at shallow depths along narrow zones. By studying earthquakes and the seismic waves they produce, scientists can map plate boundaries with great precision and understand how plates interact. Rock magnetism has been crucial to understanding seafloor spreading and continental drift, providing some of the most elegant and convincing evidence for plate tectonics. When volcanic rocks cool, whether on land or on the seafloor, magnetic minerals within them, tiny crystals of magnetite and other iron-bearing minerals, align with Earth's magnetic field and lock into place as the rock solidifies, creating a permanent record of the direction and strength of the field at that time and place. By studying this magnetic record in rocks of different ages, using instruments called magnetometers to measure the magnetic properties of rocks, scientists can determine where those rocks were located relative to Earth's magnetic poles when they formed. This technique, called paleomagnetism, has been used to track the movement of continents over hundreds of millions of years and to map the magnetic stripes on the ocean floor that provide such convincing evidence for seafloor spreading. The fossil record also provides evidence for continental drift, showing that life's history makes sense only when we understand that continents were once joined. The distribution of fossils, the geographic patterns of where different species lived and left their remains, becomes comprehensible when we realize that continents that are now separated by oceans were once part of a single landmass. Species could spread across Pangaea when the supercontinent was intact, walking or swimming or being carried by wind from one region to another, which explains why fossils of the same organisms are found on continents now separated by thousands of kilometers of ocean. The timing of when different groups of organisms appeared or went extinct can be correlated with continental movements and the resulting changes in climate and environment, showing that plate tectonics has shaped the history of life. All these lines of evidence, from GPS measurements to earthquake distributions to magnetic stripes to fossil patterns, paint a consistent picture of a dynamic Earth, a planet whose surface is in constant, slow motion, driven by heat from within. The continents have wandered across the globe throughout Earth's history, and will continue to do so far into the future, billions of years from now, when the sun will be brighter and Earth's interior will have cooled somewhat, but will still be warm enough to drive plate tectonics. Oceans have opened and closed, repeatedly, with new basins forming as old ones vanish. Mountains have risen and eroded away, reduced from towering peaks to gentle hills, their materials recycled into new rocks. Climates have changed, sometimes gradually, sometimes rapidly, in response to continental movements. And through it all, life has adapted, evolved, and persisted, shaped by the shifting continents and the environments they create. As we reach the end of this journey through the evolution of continents, it's worth reflecting on what plate tectonics means for our planet, why it matters that Earth is geologically active. Earth is geologically active in ways that make it almost unique in our solar system, setting it apart from its neighbors. Of the rocky planets and moons we've explored, only Earth has plate tectonics as we understand it, with rigid plates moving across the surface, continents drifting, oceans opening and closing. Venus has volcanism, with mountains and lava flows covering its surface, but no evidence of plate tectonics. No sign that its crust is broken into plates that move. Mars was geologically active in its distant past, with enormous volcanoes and vast canyon systems, but appears to be largely dormant now, its interior having cooled to the point where plate tectonics, if it ever existed there, has ceased. The Moon has been cold and inactive for billions of years, its surface preserving a record of ancient impacts, but showing no signs of current geological activity. Plate tectonics may be one of the key factors that makes Earth suitable for life, contributing to the planet's habitability in ways we're only beginning to appreciate. The movement of plates recycles materials between the surface and the interior, creating a planetary-scale recycling system. Subduction carries water and carbon into the mantle, preventing them from being permanently locked away in rocks, while volcanism returns these materials to the surface, replenishing the ocean and atmosphere. This recycling maintains the composition of the ocean and atmosphere over geological time, preventing them from changing in ways that might make Earth uninhabitable, keeping conditions within the range that life can tolerate. Mountain building, driven by plate tectonics and continental collisions, affects climate by changing wind and rainfall patterns in ways that influence life across entire continents. The weathering of mountains consumes carbon dioxide as rainwater dissolves minerals and carries them away, helping to regulate Earth's temperature over millions of years by removing greenhouse gases from the atmosphere. Without plate tectonics, without mountains being continually built and eroded, Earth's climate might have changed in ways that made it too hot or too cold to support life long ago. The creation of diverse habitats through continental drift, mountain building, and the opening and closing of ocean basins has driven the evolution of life in countless ways. When continents split apart, populations become isolated on separate land masses and evolve in different directions, unable to interbreed, leading to the formation of new species. When continents collide, species that evolved separately come into contact, competing and interacting in new ways, sometimes leading to extinctions, sometimes to new adaptations. The changing configuration of continents alters ocean currents and climate patterns, creating new selective pressures that drive evolution in particular directions. Some scientists have even suggested that plate tectonics is a requirement for complex life to evolve on any planet. That worlds without plate tectonics might be able to support simple microbial life, but not the kind of complex, multicellular organisms we see on Earth. If this is true, and the hypothesis is still being tested, then in our search for life on other planets orbiting other stars, we should look for worlds that show signs of plate tectonics. Worlds where we can detect the signatures of moving plates and recycling crust. Such worlds would have the kind of long-term stability and recycling of materials that seem necessary for life to not just originate, but to evolve and diversify into complex forms. Now, as you lie here in the quiet darkness, let your mind rest on these vast scales of time and space, on the knowledge that you are part of something far larger than yourself. The ground beneath you, moving, carrying you on a journey that will continue for millions of years to come, long after you are gone, long after human civilization has passed into history. The solid earth that feels so permanent beneath your body is actually in slow, constant motion, part of a great cycle that has repeated throughout our planet's history and will continue repeating for billions of years into the future. Think of the rocks beneath you, perhaps formed in an ancient ocean hundreds of millions of years ago, lifted high onto a continent during a long-ago collision between landmasses, shaped by wind and water over countless millennia, now lying quietly beneath you. Think of the mountains in the distance, slowly rising millimeter by millimeter each year, or slowly eroding grain by grain, their existence temporary on the timescale of deep time, though they seem eternal to us. Think of the oceans, vast and blue, covering pieces of crust that are simultaneously being created at mid-ocean ridges and destroyed at subduction zones, part of an endless cycle of renewal that has operated for billions of years. All of this happens too slowly for us to perceive directly, too gradually for any human to witness. Yet it is real as the breath moving in and out of your body, as real as the beating of your heart. The Earth is alive with motion, with constant change operating on timescales we can barely comprehend, and you are part of it. A passenger on this remarkable planet as it journeys around the sun and its continents slowly move across its surface, rearranging themselves in patterns that will be completely different millions of years from now. Let this knowledge bring you peace, a deep sense of calm and perspective. The problems and concerns of the day, the worries and anxieties that occupy your waking hours, are real and important to you. But they exist on such a different timescale than the movement of continents. The mountains were here long before you were born, standing tall when your ancestors walked the earth, and will remain long after you are gone, though even they will eventually erode away. The oceans have opened and closed while life evolved from single cells to the rich diversity we see today, a process spanning billions of years. The continents have wandered across the face of the earth for all of Earth's history and will continue to wander for billions more years until the sun grows old and bright and eventually makes the planet too hot for liquid water. You are a part of this ancient planet, a brief but precious part of its long story. The same elements that make up your body, the carbon and oxygen and nitrogen and calcium and iron, were forged in stars that lived and perished long before the sun was born, scattered across space in supernova explosions, and gathered together when Earth formed 4.5 billion years ago. You are made of stardust and ocean water and minerals from eroding mountains, quite literally composed of the same materials as the planet itself. You are connected to everything around you, part of a system that encompasses the entire planet and reaches back to the beginning of time. In the morning, the sun will rise, the same sun that has illuminated Earth throughout its history, that shone on Pangaea when all the continents were joined, on the dinosaurs as they walked the Earth, on the slow rise of the Himalayas, on every moment of geological time. But for now, there is only this moment, this breath, this quiet darkness embracing you. Let yourself sink into it. Let the vastness of geological time wash over you like a gentle tide, carrying away your worries and concerns. The continents will continue their slow dance across the face of the planet. Mountains will continue to rise and erode, atom by atom, grain by grain. Oceans will continue to spread at mid-ocean ridges and be consumed at subduction zones. And you, here, now, can rest, knowing that you are part of something far larger and more enduring than any single life, any single moment. You are a child of this planet, born from its ancient rocks and waters, connected to every other living thing through billions of years of shared history on this wandering Earth. Let that connection comfort you. Let the knowledge of deep time give you perspective on your own brief existence. Let the slow rhythm of geological change lull you into peaceful rest, the quiet knowledge that the Earth has been here for billions of years and will be here for billions more. The Earth continues its ancient journey through space, carrying all of us with it, and there is nowhere you need to be, nothing you need to do, but simply be here, now, resting, breathing, part of the eternal present moment. You have done enough for today. Close your eyes and know that you have done enough. The questions that occupy your mind can wait until tomorrow. The worries that weigh on your heart can rest for now. The earth beneath you is ancient and patient, and knows how to hold you safely, has been holding life safely for billions of years. Close your eyes and let yourself settle, like sediment settling to the bottom of a quiet sea, finding your place of rest. Let yourself go now, releasing your grip on the waking world and allowing sleep to carry you away like a gentle current. The continents will keep moving while you sleep, imperceptibly but inexorably. The Earth will keep turning, rotating on its axis as it has for billions of years. The stars will keep shining in the darkness above, the same stars that have watched over Earth throughout its long history. You are held by this planet, this ancient home, cradled by forces billions of years old, and you are safe. Rest now, deeply and completely. Let the slow rhythm of geological time carry you into dreams, into a place where time has no meaning, where millions of years can pass in an instant, or an instant can last forever. You are part of the Earth, and the Earth is part of you. And both of you are part of the cosmos, the great unfolding story of matter and energy that began with the Big Bang and continues in every atom of your body. Good night. Sleep well. Dream of continents wandering across ancient seas, of mountains rising toward the sky, of deep time stretching endlessly in all directions. You are home. You are safe. You are exactly where you need to be.